Welcome to Class 5. Class 5 is moderated regression with continuous variables. So, as the name suggests, we'll be talking about moderated regression. This is a shorter set of slides, so I'm going to try to do it in just one part. We'll see how that goes. I might have to divide it up, but for now we're going to try to just do it as one part. Okay, in your book, they do moderation totally through process. We are going to actually, in this class, we'll do that later. So we've divided it up. We're going to teach you how to do moderated regression first, just using SPSS regression. Then we'll teach you how to do moderation using process or using Hayes process. And the reason we do that is I think it's useful for you to know and be able to do moderated regression without using process, so you can see what's really involved in moderated regression. And also, I think, for myself, I would say not all interactions are moderations. We'll be getting into that. Although certainly Hayes's process model can handle pretty much any kind of regression that you're doing. But so our approach is going to be to teach you regression first, or doing moderated regression first, sort of the old-fashioned way, and then to teach you how to do moderated regression using Hayes's process. We're also going to do it in two classes. One class is going to cover the continuous variable situation, and the other one will handle the categorical variable situation, particularly dichotomous variables. I think for myself, I might actually reverse the order, but the order we're going to go is continuous first and categorical second. Okay, so you're probably asking yourself, well, what is moderation? Well, moderation is really just the combined effect of two variables on another, and that's known conceptually as moderation. And in statistical terms, that would be an interaction effect. Moderated regression. This is from Wiki. I thought the definition of moderated regression in Wiki was really great, so I borrowed it here. In statistics and regression analysis, moderation occurs when the relationship between two variables depends on a third variable. The third variable is referred to as the moderated variable, or simply the moderator. The effect of a moderating variable is characterized statistically as an interaction. That is, a categorical, e.g. sex, ethnicity, class, or quantitative, e.g. level of reward, variable that affects the direction and or strength of the relation between dependent and independent variables. Specifically, within a correlational analysis framework, a moderator is a third variable that affects the zero-order correlation between two other variables, or, in regression, the value of the slope of the dependent variable on the independent variable. And then, of course, in analysis of variance, it can be seen, you should know what an interaction is. It's when the two main effects don't totally explain the results. There's an interaction between those two main effects. Okay, one thing that not too many people discuss that really interests me, and I think it leads to a lot of confusion, is there a difference between interactions and moderated regression? I think yes, there is. I think there's important differences between interactions and moderated regression. I'm not going to get into what I think, all that I think about that. I mean, you have quite a few readings. And for our purposes, really, they're going to be the same. For our purposes, we're not going to see a difference between interactions and moderations. But I think conceptually there is a difference. And I will get a little bit into it. But I think conceptually there is a difference. For example, I think there's a particular type of interaction, which is really a boundary, what's called a boundary condition, not a moderator. And I think that confusion between moderators and boundary conditions leads to a lot of problems or conflicts between different camps of researchers. But not too many people in psychology, we don't talk about too often boundary conditions. In the physical sciences, they talk about boundary conditions a lot. In the social sciences, we really don't deal very often with a boundary condition. Now, what's a boundary condition, you might say? Well, boundary condition is the environment or situations in which we think our model actually operates. And probably an example I would give is a test. If you're testing somebody's knowledge of introduction to psychology, and it's a written paper and pencil test, and they can't read, then that test is not going to be valid or effective. Now, in that case, is reading level, is being able to read a moderator? No, I would say it's really a boundary condition. The boundary condition, anytime we give anyone sort of a written multiple choice test, is that test is only going to be valid if they can read well enough to understand the questions, the stems, and the alternatives. So to me, that's not a moderator situation. That's a boundary condition situation. And understanding that difference is critical. But that's sort of a more advanced topic than this class. You know, if you're out, unfortunately, because of COVID, we're meeting virtually. We can't just get together and discuss this after class or have an informal discussion of it. Even among yourselves, you can't do that. That'd be a fun topic to sort of discuss outside of class. But unfortunately, again, we can't do that. But it's one of those topics just I'm mentioning to you, maybe keep in the back of your mind, and at some time later it may make sense. Also, in terms of understanding interactions, I actually think that categorical variables are much easier to understand than continuous variables. I would actually myself reverse the order, but for historical sake, in terms of how this course has usually been taught at DePaul, I went with sort of the more traditional order, which is we're teaching categorical variables first and continuous variables second. Okay, and again, this is just following up on what I just said. To me, interaction is more of a general term. It's where something new is created. For example, many people give as an example of interaction, which is not really a moderator, but would be an interaction, is how hydrogen and oxygen interact to form water. So how hydrogen and oxygen interact to form water. They would say, now that's an interaction. Also, many boundary conditions, again, I think, cause interactions. And I think really it's an interaction anytime, it's an interaction that's not a moderator, anytime the interaction involves two equally important predictor variables of interest. To me, a moderator implies that one variable is affecting the relationship between two other variables. So a moderator to me occurs when one variable is seen as the cause or main variable of interest, and that second variable is changing that causal relationship. All right, well, let's look at some examples. Now, I'm a terrible artist. You're going to see I'm a terrible artist, and I drew these just because I wanted to express a little bit of me to you. Really, Hayes, in his book on his process book, he goes through lots of models, and his models look a lot better than my models look. But these will do for now. So our first model is just really what I would call an interaction and not a moderator. For example, a lot of people argue that ability interacts with motivation, for example, to cause grades in a psychology class. That my ability doesn't matter if I'm not motivated. But that would be that's often seen as sort of an interaction, ability and motivation. And really, I think it's not a moderator to me because motivation in this situation is more of a boundary condition. The relationship between ability and psychology grades is only going to exist if you're motivated, if you're following what I'm saying. But anyway, I mean, for what we're going to discuss here in statistics class, that's not that critical, but I'm just trying to give you my worldview on this. So I would say this is a clear interaction between independent or predictor variables, but really not necessarily a moderator situation. Now, here's what we would think of as the traditional moderator model. For example, one of the most studied relationships in psychology has been the relationship between general mental ability, often measured with things like the SAT or the ACT, and grade point average in college. And of course, one of the arguments that a lot of critics of testing make, and which we can actually do studies to test, is that various demographic variables interact or moderate the relationship between general mental ability and GPA. So that's a clear moderator model to me. You're saying general mental ability predicts GPA. It predicts it because it sort of causes my school performance. And demographic variables here serve as a moderator because people would argue, critics of testing would argue, that there's different demographic variables that moderate the relationship between general mental ability and GPA. That general mental ability is a good predictor for some individuals, but not for other individuals. Similarly, this is another sort of moderated model. Here, this is really a moderated model with mediation, which we'll talk about later. But in this model, we have general mental ability predicting job knowledge, which then predicts job performance. This is a common model we often see where general mental ability leads to the generation or gathering or accumulation of job knowledge, and then job knowledge predicts job performance. But again, critics of sort of the testing would argue that demographic variables moderate these relationships. So demographic variables can moderate the relationship between general mental ability and job knowledge, and that's because they interact. This X means interaction. I should have said that before. This X means interaction. So demographic variables interact with general mental ability, or moderate the relationship between general mental ability and job knowledge. And then demographic variables moderate the relationship between job knowledge and job performance. In this part or section, well, actually this class, because it'll be next class where we discuss categorical moderators. In this class, we're dealing with interactions between two continuous variables. Of course, it could also be two or more continuous variables. By continuous, we just mean a variable where there's a continuum of scores, probably at least 5, and we can treat it as being interval level data. I guess a better way to say it is we're saying that the variable we're dealing with is not either dichotomous or categorical. And because it's not dichotomous or categorical, there's no reason for dummy coding, which we'll talk about next class. Of course, as with an analysis of variance, if you remember back to analysis of variance, the problem in analysis of variance is often when you get an interaction, how do you interpret it? Can you interpret the main effects anymore? Usually you say no. How do you interpret that interaction? It's often not that easy. So the problem in regression, as with an analysis of variance, is what to do if the interaction is significant. And it's actually harder to interpret interactions when the variables are continuous. That's why I have so many question marks, because there's so many issues or questions. Okay, so for example, we might want to look at, do violent video games make people antisocial? We have a study, we have 442 young people, youth, that we've collected data on. And our outcome variable is going to be aggression. And then we're going to have a moderator that's conscientiousness, one of the big 5. And we're going to have an independent variable that is number of hours spent playing video games per week. So that's our basic model. Our model is we have an outcome or dependent variable, aggression. We have a moderator, conscientiousness. And we have an independent variable, number of hours spent playing video video games per week. So conceptually, our moderation model would look like this. The moderator moderates between the predictor and the outcome, or between the independent variable and the dependent variable. So if conscientiousness were a moderator, then we're saying that the strength or direction of the relationship between game playing and aggression is affected by C or conscientiousness. But statistically, the moderation model looks something like this. Statistically, we actually have three variables affecting the outcome. And the three variables are the predictor, the moderator, and the predictor times the moderator, or the interaction of the predictor and the moderator. So statistically, it just looks like we have a main effect for the predictor, a main effect for the moderator, and then the interaction of the predictor and the moderator. But we know in our mind that conceptually we've created this as a moderated model. All right, one of the problems is, of course, to use continuous variables in interaction, we have to standardize. We have to center the variables. And so it's pretty easy to create centered variables. All you do is subtract the mean. So if we want to create a centered variable, all we have to do is subtract the mean. Although I always say, well, you could just standardize the variables, but then you lose the units. So if in SPSS, if we're doing moderation, if we want to do it ourselves, now as Field points out, there's some programs, including process, that will create the interactions themselves. There's also an automatic option in SPSS that will create the interactions themselves. But I think it's better for you to get practice doing it. So to get practice doing it, it's a two-step process to create an interaction. First, we have to center the variables. So we create the center variables. And that's really easy. We just subtract the mean. And then we have to multiply the centered variables together. That's pretty easy. Again, we just multiply. So the interaction would be compute AB equals A times B in SPSS. So we can just call up, the transformation, the compute statement, and say AB equals A times B once we've centered the variables. So again, it's a two-step process. Center the variables, which does not mean standardizing them, although I think that's sort of an easy way to center them, but it loses the units of the measure. So what we do is we just subtract out the mean from each of the variables, and then we multiply them together to create a new variable. So, and why do we center? Well, again, it aids in interpretation. The interaction terms makes the B's for the main predictors uninterpretable in many situations. So for this reason, it's common to transform the predictors using grand mean centering. So again, the way I phrased that may not have been the best when I was reading it. If we don't center the variables, then the interaction term is often sort of uninterpretable. So by centering, by using what's called grand mean centering, we can transform the predictors and we make the results more interpretable, because basically what we're looking at is one variable at the 0 point of the other variable. Fields probably has a better explanation of this than I'm giving. I think if you read it over several times, you'll probably understand it. It's a little hard to explain, but centering eliminates those problems. Although, as I said, one thing Field doesn't point out is that there might be some transformation that would completely eliminate that interaction effect if it's an ordinal interaction. So centering is just the process of transforming a variable into deviations around a fixed point. So centering is often seen as important. The book argues it's important. I will say I sometimes have my own sort of philosophical issues with centering. Again, to me, if the way you have your variables scaled, like say you have two Likert scales, 1 through 5, Well, if you center those, you're really losing that interpretation of them being 1 through 5. Even though you still have the same units, they're not 1 to 5 anymore. Now they're, say, -2 to 2. So I have a little issue there, but I say, okay. Sometimes I say, well, if you're going to go ahead and center, why not just create z-scores? Well, because the answer I know myself is because then you lose the units, but creating z-scores may be a lot easier, especially since when a lot of people go to graph or interpret their results, they often use z-scores. So when a lot of people go to interpret their results or to graph them to interpret their results, they convert them to z-scores. So then I said, well, why not just turn them into z-scores in the first place? But there's people smarter than me. Like you'll see Hayes, for example, in his process model, he believes it's better to interpret things in terms of B's than betas. Now, I know there's people who disagree with him. I'm not sure. I'm not enough of an expert on moderation mediation to totally even understand his arguments, but I can appreciate his arguments. And so I see what he's saying. You want to retain the units. So I think the best advice is probably not to listen to me and my philosophical wanderings, but to go ahead with centering the way it's suggested, if you're going to do interactions of continuous variables, you need to center. So the procedure then for centering is simply to get your descriptives for your variables. Of course, you need the mean. Subtract the mean from every score, which calculated, of course, gives you a new centered score. And then you can create interactions out of those center scores. And you can create as many as you need, either a two-way interaction, multiple two-way interactions, three-way interactions, four-way interactions, however many you need. I will say, though, I don't see too many studies that involve more than a three-way interaction. And it's probably typical that you don't really have more than a two-way interaction, especially when you're dealing with continuous variables. Now, maybe for categorical variables, yes. But for three-way, for categorical variables, for continuous variables, you don't see many situations where you really use more than a two-way interaction. So let's do a simple interaction here, a moderated regression analysis. Now, we're not using field. The reason we're not using field is because field doesn't use SPSS to do moderated regression. Field uses process. So we're going to do process later on, and then we'll use field. But for right now, we're going to use our own data. So what we want to look at is a moderated regression where we look at the interaction of density and temperature in predicting deaths per population from COVID. So to do this, what we had to do was first center density and center temperature. Then we multiply the two of them together, and then we can run the regression. So that's what we did. So sort of like a cooking show, I've already put some of the food in the oven and now I'm taking it out. So I already did the centering of the variables and I already created the interactions, and now I'm taking them out to run the regression. So again, in SPSS, we just say analyze regression linear, same as when we're running a simple linear regression. Although again, we're not running a simple linear regression, we're running a moderated regression. Okay, so again, we're using our COVID data set for the states. There's 50 states. You can see in this case, we're going ahead. I'm using deaths per population here. As I said, I'm not very obsessive compulsive. I switch back and forth. This variable is actually COVID deaths per million rather than COVID deaths per 100,000. And then I created two centered variables, centered temperature, which is the temperature, average temperature in the state, but centered, and centered density, which is the density per square mile centered. And then I created an interaction by multiplying together centered density and centered temperature. So then the next thing I did was to run the two models. Now, what I usually do, again, I should have mentioned on the last slide, but one thing I usually do is I usually enter the two main effects, or the moderator and the predictor, on step 1. And then the interaction gets added in step 2. So I do it as a hierarchical regression, putting in the center temperature and center density on step 1, and then adding in the interaction on step 2. You could actually argue you could do this in 3 steps. Enter in the main variable you think is the cause, say center density, and then adding in center temperature in the second step, and then adding in the interaction in the third step. One of the reasons you might do it 2 steps is a lot of times you're probably going to want to use both variables in your equation, in your final equation, but you're going to drop the interaction if it's not significant. So a lot of times you might drop the interaction if it's not significant. Now, there was one other thing I wanted to say. Of course, we also have the constant in here. We do also have the constant in this equation. So again, actually in step 1, I enter the constant center temperature, center density. Step 2, I enter the constant center temperature, center density, and the interaction of temperature and density. And step 3, or I'm sorry, the dependent variable is the number of deaths per population, COVID deaths per million people. One other thing I should add in is that I guess why am I doing this? That's probably the best question. Is there a reason I'm doing this? Well, again, I've tried to base this on real hypotheses people have had. And so, of course, there was a hypothesis that in warmer temperatures, COVID would be less severe. That probably didn't play out, but I thought it might be interesting to see if temperature did interact with density. So I thought that might be interesting to look at. And you can see it actually turns out it's true. Now, again, we're doing this at the state level, so you really have to be cautious in making any interpretations. I'll keep repeating that. You know, it's not at an individual level, it's not at a county level, it's at the state level. I wasn't getting paid to create this data set and to do this analysis. I sort of just did it out of interest. And so I wasn't going to go down to the county or the city or the individual level. But I think it's still interesting. I just think you have to be careful of the interpretations you make. So when we look at this, we can see our R squared here is 0.547. When we put in both center temperature and center density, it's significant. Now, what's interesting is when we put in the interaction, it's also significant. It's still significant. The associated p-value is 0.020, which is significant at the 0.05 level. So there is evidence that temperature is moderating the effect of density on COVID deaths per million. Here's our ANOVA table. You can take a look at it. Our sum of squares, again, sum of squares regression and sum of squares residual add to sum of squares total. Here's our degrees of freedom. We had 50 states, so our total is 49. We have 3 predictors in the model, so here our degrees of freedom are 2. Here we have 4, so it's 3. The residual is 47 and 46. The mean square is simply the sum of squares divided by the degrees of freedom. The F is simply the mean square for residual regression divided by the mean square residual. So the F is mean square regression divided by mean square residual. And then, of course, SPSF looks up the probability level associated with that F and those degrees of freedom. And we can see that both Model 1 and Model 2 have a p-value of 0.000. And then we can look at the coefficients. Unfortunately, density's cut off, but unfortunately, the interaction's cut off. But I'll tell you, it is significant, so that you're not worried. It is significant. So what we want to look at is Model 2. And when we look at Model 2, we can see that the main effect well, of course, if we want to look at everything in the model, here's the B for our constant. Here's the B for center density. Here's the B for center temperature, and here's the B for the interaction. You notice, of course, as temperature goes up, deaths go down, although in this regression, it's not significant. So when we look over here and one's cut off, it actually turns out that the centered density is significant. Centered temperature is not significant. But again, the interaction of temperature and density is significant. So whosever idea this was right. In fact, the effect of density on COVID deaths at the state level is impacted by the interaction of density and temperature. Now, how do we interpret that? Well, probably the easiest way to do is graph it. So what I did, I went into Excel and I just created or estimated values so that I could graph this. So you can say I sort of created a simple Excel worksheet where I have the value at the I have the predicted value, and these are all standardized. So this is the mean for temperature, 1 standard deviation above the mean, 1 standard deviation below. The mean for density, 1 standard deviation below for density, 1 standard deviation above. And then these would be standardized COVID deaths per million. So it's standardized COVID deaths per million. So I standardize things so that it would make it easier to graph them. And I actually did this in Excel. So I used that regression line to come up with these values in Excel. And then the reason I did that is Excel, I thought, does a better job of graphing these kinds of things than does SPSS. As a matter of fact, I think unless you're an expert in graphing in R, I know a lot of people who argue it's easier to graph these interactions in Excel than in either R or SPSS. And Excel offers you more options in terms of making this look pretty. I don't know if that's true. I'll leave it to Jason to talk about whether that's true or not. But I just know people who claim it. I'm not that much of a graphing expert. I'm just passing that along to you. But so when we look at this, we can see the interaction, right? I mean, temperature itself does not have much of an effect on deaths per million or on COVID deaths. But this would be our different density lines. And it's cut off here, the density coding. But at the lowest level of temperature, density makes a huge difference. So this would be 1 standard deviation above the mean in terms of density, the mean in terms of density, and 1 standard deviation below the mean in terms of density. So you can see when temperature is low, like it is in the north, although there's some southern states, surprisingly, that have fairly low temperatures. But so when temperature is low, when the average temperature is low, density makes a huge difference. When temperature is high, density makes no difference. And then, of course, in the middle, when temperature is average, density makes a difference, but not as big a difference as when temperature is low. So density is much more of a factor when the temperature is low. Again, I'm not going to interpret that. I don't want to get into overinterpretation of these findings. I'm not a disease specialist. Now, depending upon your theory and your interest, you could always change this around and post it the other way. And so if we change it around, we can see that the effect of temperature sort of changes depending upon the density. Actually, now here, we do have our X type of interaction. So we do have our X type of interaction, a disorderly interaction. And what we can see is that when we look at this chart, when density is high, then temperature makes a big difference. This blue line is low temperature. So this blue line is low temperature. So if density is low, then a low temperature actually results in the least number of COVID deaths. On the other hand, if density is high, then a low temperature results in the highest number of COVID deaths. So when density is high, this would be average temperature, or this would be, high temperature, average temperature, low temperature. And so you can see that when density is high, your temperature makes the biggest difference. So when density is high, a low temperature has the biggest effect compared to either an average temperature or a high temperature. On the other hand, what's sort of interesting here is if density is low, then a low temperature actually results in the smallest number of predicted deaths. Now, one thing I should add here, though, always with interpret things, these are predicted values. They're not necessarily observed values. I mean, you might find no values that actually match these lines. So these are predicted values, not actual observed values. But in terms of the predicted values, again, we would say that, hey, your troublesome combination is when you have high density and low temperature. If you have high density and low temperature, it's going to be a problem. If you have low density, then, well, actually, they all have below average deaths, but with low density, low temperature results in the lowest number of COVID deaths per million. So again, I don't think you want to overinterpret this. It's only 50 states. And there's probably a lot of other unique factors operating or going on, but I thought that was somewhat interesting. And then finally, I actually did sort of a 3D plot of temperature and density just for fun. Okay, that's the end of moderated regression. And this is sort of interesting. This is an earth-friendly straw. It's a straw that's not made out of plastic. It's a straw that's made out of paper. But again, we're to the end, so you can always email me at dennisdoverspike@gmail.com.